This interactive climate project focuses on Earth's climatic history from the present back in time to 550 million years ago. 3 aspects of Earth's climate history are depicted. They are temperature, carbon dioxide, and sea level. These 3 items are depicted in graphical form. These charts are presented in a synchronized manner over a 5-panel presentation, each panel covering a different period of time. We're currently looking at the first panel. It covers a period of time from the present at the left back in time 20,000 years on the right edge. In this panel, the temperature graph is shown in blue. That's this graph here. The CO2 graph is shown in green. That's this line here. The sea level graph is shown in black. That's this line here. There is a letter X that overlays the temperature chart. The purpose of this X is to indicate time advancement as one interacts with the project. I can cause the X to move, like such, and what it does is it advances the time period that you're looking at in the chart range. If you look over top the X, you will see the corresponding values of both CO2 and sea level at those times. Also, this blue box will indicate the current time period in years. In this case, 6,000 to 7,000 years ago. As we travel back in time for 240 million years, there will also be a panel that displays the position of the continents or continental drifting. Specifically, we will be able to view the breakup of the last supercontinent called Pangaea, and occasionally important events will be displayed. In this example, this blue box here is indicating that at this point in time, we are currently in an official ice age, and there is both an Antarctic and a Greenland ice sheet. Now, each graph for temperature CO2 and sea level has their own scale to go along with them. For example, the temperature graph here is defined by the temperature scale, which you see here. 0 is the current temperature average, which was basically an average drawn from temperatures from 1960 to 1990. That's considered the average temperature over time. The CO2 chart uses this scale here to depict CO2 values in parts per million. For example, right about here, the CO2 is sitting at about 280 parts per million. Sea level is defined by this scale here. 0 at top here is the present sea level value going back in time. The sea level chart, in this case, is depicted as going down in value from 0 to minus 140 meters. And that's because as we go back in time, we will see the sea level drop substantially. So we have temperature in degrees Fahrenheit CO2 in parts per million and sea level in values measured in meters. Here, we've advanced to the second panel. The second panel covers a time span on the left side here from 20,000 years ago back to 1 million years ago on the far right. Basically, the period of time from left to right is 980,000 years. Again, we have 3 items presented. We have a temperature curve. In this case, it's this blue and black graph here. We have CO2, which is this lighter blue graph here. And we have sea level, which is this black graph you see here. Again, the scales for the 3 graphs are different. Temperature is what we had before right here, 0 plus 25, and down to minus 10. We have CO2 here. Its scale is over here to the right, and we have sea level. And sea level scale is right here, going from plus 20 down to 0, down to minus 140. Again, sea level is in meters. Temperature is in degrees Fahrenheit. CO2 parts per million. Now, the second panel actually is presented in 2 phases. This is the first phase. That's because we have this light blue CO2 graph. However, I've now advanced to the second phase of the second panel. In this case, we have this very large CO2 curve on the top here. Note that it has a different scale up here on the left. Also note that there's this little red splotch here. If I zoom in, you can see the red splotch there. That red splotch means that the time span represented by this period here, which is 200,000 years from 800,000 years ago to 1 million years ago. This time span of the temperature graph is represented by the width of this red bar you see here, which basically indicates what part of this curve we're referring to. This red bar only points to this little section up here, and it was not possible to expand that and have a useful chart to look at. Here, we've advanced to the third panel. Note the temperature graph is in black. There is no sea level chart in this panel because there was no chart available to use. However, we are looking at the same CO2 chart as the second half of the second panel. Note, however, that the red bar which is indicating the period of this graph that pertains to this panel is wider. This span of red bar equals the span of the entire temperature chart down here. Again, we have a temperature scale here. 0 being the average from 1960 to 1990, and we have a CO2 scale. Here, we've navigated to the fourth panel. Time span here goes from 5.5 million years on the left to 65 million years on the right. Again, temperature is depicted in green, CO2 up here in blue. This time we have a sea level graph. That's the red line you see here. Once again, here's our temperature scale, 0. Being right here going up to plus 25, and CO2, here's the scale here. And sea level, here's its scale here. Note the sea level here goes from 0 up to 400 meters. Here, we've navigated to the fifth panel of our project. In this panel, the yellow-red graph here is the temperature line. It goes up and down. It actually goes all over the place. Temperature gauges here. Again, going from about -10 up to plus 25. The CO2 chart is changed dramatically. Instead of a single line, we have a number of various estimated lines. The most probable line that you should pay attention to is this kind of orange-colored one you see here. This is the most likely value of CO2 during various periods of time in this particular panel. Sea level has this red graph here. The sea level scale is here. Again, going from 0 being today's value down here up to 400 meters and going negative. However, sea levels here, carbon dioxide here. Note that the carbon dioxide scale on this particular chart goes up to a much higher level. And that's because carbon dioxide in the atmosphere was extremely high at the end of this panel, which is 550 million years in the past. I'll also point out that if as we go through these panels, you will begin to see, particularly in this last panel, as we span the time frame, you'll be able to see the continents changing position from their mostly current position into what was the last supercontinent called Pangaea. Here, I've navigated the project all the way back in time to 550 million years ago. I've also reconfigured the project so that we're only looking at the temperature graph and the CO2 graph. This makes it easier to understand what we're going to be seeing. Again, here's our temperature gauge, and here's our carbon dioxide gauge. Here's our X. The X marks the time span we're in. In this case, we're currently sitting on a time span 549 to 550 million years ago. First thing I'll point out is that if you follow this line, it just happens to be here by luck. At this point in time, let's see if we can get the X over that. Right about there. Right about there. We go over here to the temperature curve. We can see that the temperature of the Earth at that point in time, and that's 535 million years ago, that temperature was about 27 degrees warmer than it is today. It's also obvious that CO2 is much higher than it is today. I'm going to bring down a little item that allows me to do a horizontal compare. I'm going to put this line right at the top of the CO2 peak, which is over X. And if I follow it across, you can see that the CO2 value here is approximately 6,800 parts per million. And that compares to 410 parts per million in the present time. And again, temperature 535 million years ago is about 27 degrees higher than today. CO2 is way up there at 6,800. Now, before going further, if we look at the temperature chart as it goes along here, it's pretty obvious that almost all the time during this period, and that's from 65 million years ago here to 550 million years ago over here, almost all of that time is spent with the Earth being much warmer than it is today, where the 0 line is here. There's only one period of time, and that's here, and that's going to turn out to have been another ice age, where temperatures were colder. So now if I go ahead and move our X forward in time, watching the time here, you can see that as we move along, we run into another period of time around 450 million years ago, where Earth is actually in what has been determined to be another ice age. It's not very long. As I recall, it was about 30 million years, but it definitely happened. And make note that it happened when temperature was about 10 degrees warmer than today, and CO2 was running about 4,500 parts per million compared to 410 today. We're going to go on back and move forward in time. And as we get down to this low point, we're going to run into another ice age. This ice age lasts for about 100 million years. And as you can see, the temperature dropped to the lowest level that we've seen in recent history. CO2 is close to our current value. Current value is 410. Here, it's about 400. Only when CO2 dropped that low did this part of the time span enter an ice age. I'm going to go ahead and continue to move forward in time. We're out of our ice age, and if you kept track of the time, that ice age would have lasted about 100 million years. We'll go up, and now in about 240 million years, we pick up our depiction of plate tectonics breaking up the last supercontinent, which is Pangaea, and that's this thing here. Then as we move forward in time, you can see that Pangaea begins to break up. And Pangaea's breaking up is going to play a critical role in setting Earth up and configuring it to where our modern climate comes about. So here we are back to 65 million years ago. The continents, for the most part, are looking similar to their current location. Note that India is still not attached to Asia yet. However, I'll point out that Australia and South America are still attached to this landmass down here, which will become Antarctica. Here, I've reset the project. We're at the end of the fourth panel. In this case, we're at about 65 million years in the past. This was also about the point in time when the big asteroid hit the Earth and killed off almost all the dinosaurs, except for a few of them that were able to fly at that time. Those dinosaurs would go on to become today's birds. Note that this particular panel covers a period of time of 59.5 million years from the left to the right. In this panel, the temperature graph, the green line, is the same as the CO2 up here that is over top this red bar here. So this temperature here is this CO2 value here. This temperature here is this CO2 here. And you'll note that we have a couple of real spikes both in temperature and CO2. This one lasted a few million years, but it was really steep. And the same happened with CO2. Again, I'll point out that 65 million years ago, India was still not attached to Asia, and Australia and the tip of South America were still attached to this piece of land here, again, which is going to become Antarctica. So, I'm going to go ahead and begin to move the time scale back, and let's see basically what happens. Start to move the X. There it goes up. You watch the time range here. It's a couple million years. It's a very short period of time, and it just comes down. I'm having to do this section manually. By the way, you'll notice this event that happens here. It says the Drake Passage and the Tasman Seaway open up, creating the Antarctic Circumpolar Current. Now, the Drake Passage is the body of water that now lies between the tip of South America and Antarctic itself. The Tasman Seaway is the passage of water that's south of Australia that separates it from Antarctica. Now, when both of those things opened up, it allowed for the creation of a special ocean circulation path called the Antarctic Circumpolar Current. And that current goes around and around Antarctica, and that allowed for Antarctica to become a very cold place, which allowed it for the first time to acquire a permanent ice sheet. And if we go back a little bit more, we can see that around 33 million years ago, we were in another ice age, and that's because that's when Antarctica first picked up a permanent ice sheet, and it will keep that all the way and forward in time to the present date. I'm going to point out that even though we have an ice age and that there's now an ice sheet in Antarctica, Earth's temperature is really warm. It's 8 to 10 degrees warmer than today, and CO2 values are very high. We're looking at about 800 parts per million compared to 410 today. So CO2 was double what it is today. Temperature was 9 degrees warmer, 10 degrees warmer than today, and yet we still entered an ice age, and Antarctica picked up an ice sheet. I'm going to continue to this along here, and we've ended up at 5.5 million years ago. And even at 5.5 million years ago, if we look at the CO2 gauge, we're looking at about 550 parts per million on the CO2, and we're looking at approximately 6 degrees warmer than today. Again, if we scrub back, I want you to keep an eye on India. You'll see that the India subcontinent has slammed into Asia. There we go. It's there now. And when that happened, that also caused the Himalayas to form. The Himalayas pushed up a lot of land, and that land being pushed up also is having a dramatic effect on our current climate. It makes it colder and drier. So we'll go back here, and we're at the end of this particular panel. Again, sitting at 5.5 million years in the past. Here, I reset the project to the end of the third panel. We are sitting at about 5.5 million years in the past. Here's the X. And again, this temperature graph going forward to 1 million years ago, here back to 5.5 million years ago. This temperature range here is represented by this red bar here on this CO2 scale. So what I'm going to do now is walk this back, pay attention to how dramatic the temperature changes in periods of time as this goes along. So let's see what happens. Now it is accepted scientifically now that the primary forcing agent for changes in Earth's temperature is really changes in Earth's orbit around the sun. Those changes are basically referred to as Milankovitch cycles, and they have a lot to do with the Earth's orbit around the Sun going from circular to elliptical, the tilt of the Earth's axis, and the precession of the axis in a circle. All of these work together and often reinforce each other and sometimes work against each other. These changes affect how much solar radiation actually fall on the Earth over time. Particularly, the most effective part of the Earth for changes in Earth's climate is at 65 degrees north and south latitudes up near the poles, because of the way the tilt of the Earth either gives them longer or shorter days in their summers and winters. I'll also point out that right about now, somewhere around 4.5 million years ago, the Isthmus of Panama, that's up here, Isthmus of Panama was formed. Prior to that, it was open. The North and South America were not connected. When they weren't connected, the Atlantic and the Pacific Ocean were allowed to intermix, and that affected ocean temperatures. The Isthmus of Panama, it's speculated, took about 1.5 million years to form. But after it did, it blocked off those waters mixing. And what it did was, it's caused warm water to create what's now called the Gulf Stream. And that warm water now circulates up towards northwest Europe. But in the process, it brings moist air up to the rest of Greenland and up into this part of Canada. And that caused more snow. And what's going to happen is after the Isthmus of Panama was formed, and that circulation between the Atlantic and Pacific ended, then Greenland will develop a permanent ice sheet. And if we continue along our little temperature path here, we'll keep watching. Let's see what happens when the isthmus is fully formed, and I think that's around maybe 3.3 million if I remember right. And bear in mind, these deviations in temperature you're seeing here are primarily caused by changes in issues related to the Earth's orbit. And again, this line here is average temperature 1960 to 1990. So from here to here, we've been mostly above our current temperature, sitting at about 3 million years ago. The Isthmus of Panama has been closed off. Now there's a land bridge between North and South America. Antarctica has its ice sheet, and pretty soon Greenland's gonna pick up an ice sheet. Let's see if we can see when that happened. There it is. Somewhere around 2.8 million years ago, the project suggests that that's when Greenland picked up its ice sheet. And again, that was because the Gulf Stream formed, started pumping warm water up into the northwest Atlantic. That put a lot of moisture up near Greenland and this part of Canada. A lot of snows began to fall in the winter, and that created the ice sheet around Greenland. So now we're in the same ice age we picked up about 33 million years ago. But now we have a permanent ice sheet on Antarctica. And we have one on Greenland now. As previously mentioned, changes in the Earth's orbit called Milankovitch cycles were due to slight changes in the orbit of the Earth as it goes around the Sun. For the period of time from about here, 2.8 million down to the beginning of this chart at 1 million, these temperature deviations were happening basically on about a 41,000-year cycle. That meant that over a 41,000-year cycle, we would enter a warm period, and then temperatures would get really cold, glaciers would form, an ice age, glaciers would advance, ice sheet would get larger, glaciers would form all over the northern hemisphere, and that would happen on a 41,000-year cycle. That's going to continue until about 1 million years ago. After that, the cycle for Milankovitch is going to change to a 100,000-year cycle, and that has everything to do with the difference between how the Earth's orbit, inclination, and precession interact with each other on a different cycle. Also, I'll point out that starting about here, about 2.8 million years ago, Earth's climate is going to drop from always above our average temperature today to almost always below. And we're going to be looking at a much colder climate for the Earth. So let's go ahead and keep walking forward in time. Again, these up and down motions of the X indicate temperature cycles again on about a 41,000-year basis. I'll also point out that there's almost no more plate tectonics. The layout of the land on the Earth is about the same as it is today. I've reset the project again. We're now at the end of the second panel. We're sitting back at 1 million years ago. Again, blue-black is the temperature chart. CO2 up top here. In this section here, this little black section of temperature is only pertaining to the area of the CO2 chart up here that's over top of this red splot. so it's really not very useful. However, note that the up and down cycles have changed dramatically. They're not so close together. That's because the major bumps have gone from 41,000 years to 100,000 years. So if we continue to go forward in time, we're going to see the temperature again staying generally on average colder than our current temperature. What is happening is that we're going to go into the warmest part called an interglacial. And by the way, we're in an ice age. Greenland has ice sheets. There's glaciers all over the northern hemisphere. And as the temperature goes down, as time goes forward, glaciers advance and retreat, advance and retreat, advance and retreat. This is called an interglacial. That's the warmest part of the cycle. Here, you can see back about 1 million years ago, those warm periods were barely equal to today's temperature. And they got cold, much colder than today, basically about 7 degrees lower than today. Only in the last 4 cycles. Again, going from 20,000 years ago to 1 million years in the right. Notice that these interglacial peaks are warmer than we are today. We're looking at almost 3 degrees Fahrenheit as the peak temperature. And some of these interglacials lasted for 20,000 years. So let's go ahead and walk the temperature curve and see how things change. We're not going to be able to see what CO2 did because we don't have a good chart for that at this point between here and here. So watch the temperature change. Up and down. Up and down, up and down. When we get to the blue curve, we change to the first part of the second panel, which gives us a better CO2 chart to look at. Here we can see the CO2 going up and down as temperature went up and down. Again, I want to point out that during these interglacials, Earth's temperature was 3 degrees higher than today, yet CO2 was colder than today. So keep that in mind as you watch where the temperature goes. And, by the way, also keep in mind, it's about 100,000 years from here to here. This is about 20,000 years. 100,000 years. About 20,000. There's a little bump here, but you get the idea. 20,000 on the way up, 100,000 years on the way down. So let's go ahead and play this. Just keep in mind that there are glaciers all over North America while this is happening, and we're at the beginning of the second panel here, or 20,000 years ago. I've reset the project again. We're at the end of the first panel. We're at about 20,000 years in the past. Here's our X. Note that the temperature here at this point is called the last glacial maximum. That's where the ice sheets in North America were at their greatest extent. Notice how cold it is? We're looking about 8 degrees Fahrenheit colder than today. And if we go up here and look at CO2, CO2 is riding around 180 parts per million compared to the average for most of the last 1,000 years of 280. Even though there's been a spike in CO2, over the last couple hundred years up to 410, we haven't seen that gigantic spike in temperature at all. In fact, it's unusual to see that the Earth actually had this relatively stable temperature period here for the last maybe 10,000 years. And again, at the coolest point here, that's called our glacial maximum. At the warmest point here, that's called an interglacial. And I'm going to point out that as we walk forward in time and we start to warm up and the glaciers start to shrink, note that at this point in time, around 14,000 years ago, there was a reversal. Something happened. The Earth got colder. Glaciers started coming back. Temperature went down. Something happened again. That reversed. And we finally warmed back up to our current temperature. And I'll point out that this little glitch here in this interglacial walk up here was called the Younger Dryas, and it's not clear at all what caused that. Although the suspicion is that the Gulf Stream temporarily stopped working right, and that cut off the flow of warm air up in this area, which affected why the climate got colder. But there's a lot of uncertainty about this, and the science isn't really sure exactly what caused the Younger Dryas. We'll go ahead and continue our X. Doesn't take long to get back there, and that's simply because walking back in time, only 20,000 years, doesn't take very long. We'll go back to the end and we'll walk it manually. And you can see that we arrived back to the present. Here, I reconfigured the chart. I've hidden the CO2 part of the chart and I redisplayed. the sea level part of the chart, as well as leaving the temperature there. So we're now going to be looking at temperature versus sea level over time. I've placed this at the very end of the 5th panel. So we're sitting about 550 million years ago. Again, note that the temperature here is maybe 22 degrees Fahrenheit warmer than today. Sea level is shown at 100 meters above today's level. Now, I'll point out that sea level is an interesting item. It changes dramatically as plate tectonics has rearranged the land masses of the Earth, as supercontinents came and went, and there have been a number of them. That change alone would change the sea level, and those changes had nothing to do with temperature or CO2. They just had to do with physical configuration of the oceans. Now you can see that we're really, really warm here. And if we walk back in time, as we get to the point where there's going to be an ice age somewhere here, and there it is. Note that sea level is about 300 and some meters higher than today, and temperature is 12 degrees higher than today. And that's just the way it was 456 million years ago. Nothing bad about it. It had nothing to do with temperature. It's just the way things happened. So we'll walk forward in time. We're out of that ice age, and it was short. Maybe 30 million years. You'll notice that there's not a whole lot of direct correlation between the temperature curve and the sea level curve. And again, a lot has to do with the drifting of the continents. So, we'll come on forward here now. We'll get back to where there's another ice age, and that's about here. You can see it depicted down here. Again, we're at about the same temperatures we are today. Sea level is 250 meters above today's level. Even though we're in an ice age where there's lots of glaciers happening all over the world, they're just not happening in the same place that they currently are. Those ice sheets over the North and South poles aren't happening there because there's no landmass over the South Pole, and the configuration of the North Pole is a wide open ocean as opposed to a closed ocean. So the ice ages were happening, but glaciers were forming and coming and going over different parts of the Earth. So we'll keep going forward here. And this ice age lasted about 100 million years, if I recall, and we're out of it. Again, look here how high we are in temperature. Almost 20 degrees above today. We've picked up our Pangea, finally. And yet sea level is down to where it is today at 0 meters. This is the only point in all this time, which is 485 million years from left to right. This is the only place where sea level came about the same as our current sea level. The rest of the time it was mostly above where we currently are. So I'll continue walking forward in time, and you'll again pay attention to the breakup for the continents. They will play a key role on sea level, because as the continents break up, they create more shoreline, more shallows, and change the sea level. That brings us to the beginning of the 5th panel. Temperature, sea level. Again, even here, we're about 120 meters higher than today, with a temperature of 10 degrees higher than today. Here, we're at the end of the 4th panel, 65 million years ago. Again, this is where the big asteroid hit and wiped out the dinosaurs. Notice the temperature is high, sea level's high compared to today. So we'll go ahead and walk forward. Okay. We're going to walk this peak, and we'll see what happens temperature-wise. And we're not going to see an obvious big change in sea level because of the temperature spike. So here we go. Go up and down. And again, we're spanning a couple million years here, but nothing obvious happening in the sea level department. So we'll continue trying to walk the temperature forward in time. Not really easy to do. Again, we're remaining above normal for today. We're in the period of time where those passages have closed here and here. We're in an ice age because there's now an ice sheet over Antarctica. And again, temperature is high and sea level is higher than today. Maybe 60, 50, 60 meters. So we'll keep going back. We're at the beginning of the 4th panel. At 5.5 million years. Temperature is about 5 degrees higher than today. Sea level is down here, and it's close to what it is today. I've reset the project so that we're at the end of the 3rd panel. We do have temperature, but there is no sea level graph to look at anywhere in this panel. So I'm going to reset this to the end of the second panel, and we do have a sea level to look at starting at about this location, and that's at about 200,000 years. I'm going to go ahead and move the X along the temperature curve until we get to sea level graph here. And again, in sea level here, we have 0 sea level value up here, going negative to minus 140. And right next to it, here's the temperature gauge. 0 being this black line is today's temperature, and going down to maybe minus 8. You can see here, again, temperature graph, sea level graph. Let me go ahead and move that X down there so we can start making some comparisons. Okay, here we are at around 200,000 years. These interglacials are about every 125 because you got 100,000 years getting colder, 20,000 years getting warmer. At this sea level peak here, we're about here. You can see how cold it is, yet sea level is still close to where it is today. But as we go forward in time, only a little bit here down the temperature curve. And by the way, this is going to take 80,000 years or so. As we do that, sea level's going to drop dramatically from just below today's value at 0 to, my gosh, about 120 meters. That's 380 feet. So that's a lot. So let's walk it over. Stop. Went too far, but you can see it there. Now, we're going to walk up the next warming section towards the next inner interglacial, which is up here. And at that point, we're at the interglacial here. That's the warmest temperature. We're 2 degrees above today, maybe 3 degrees above today's level. And sea level, though, was 8 meters higher than today's level. 8 meters is like 27 feet. The last interglacial, which is 125,000 years ago, that period of time equivalent to what we should be experiencing, was maybe 3 degrees warmer on average. And we were looking at a sea level 27 feet higher than we are today. We're going to go ahead and advance to the next panel. And here, we're now at the end of the first panel. We're just past the point of glacial maximum. That's when the glaciers were at their most in the northern hemisphere. It's cold. You can see we're running almost 8 degrees below today's average temperature, and we're getting ready to raise up sea level. Sea level is sitting somewhere close to minus 120 meters. That's a lot. And we're gonna, over the next 20,000 years, because we're going back from 20,000 to present, over the next 20,000 years, we're gonna see temperature get up to current average, and then sea level gradually go on up to our level. And I want you to note that even though we reach our average temperature here, sea level is gonna have a lot of gaining. It's gonna go up another 50 meters from here to here, even though the temperature didn't change. So let's see what happens as we walk this over. Keep an eye on the sea level chart over top of the X. We're still in an ice age, and we got ice caps on both Antarctica and Greenland. And again, here we are at today's temperature, and you can see that sea level is really low, maybe almost 60 meters below today. Even though, as we walk forward, temperature is really not a factor. It's going to go down a little bit here. It's not changing that much. Sea level is going up until just about here, it's reached its current level, the 0 value. So today's number, and it's gonna stay that way all the way up to the present.